Hello, 7th graders. Today we are looking at lesson 3-4. I can identify and classify numbers in the real number system. This is something we talked about before. We talked about rational numbers. Today we're going to get into irrational numbers as well. Following along with your book, we are on page 155. And again, my smartboard is down for the count, so I will be using my mouse today. So if my handwriting is a little bit squeamish, please bear with me. So the real number system. Numbers that can be written as fractions are called rational numbers. We learned that back in chapter 2. So rational numbers are numbers that can be written as fractions. 3/4, a whole number can be written as a fraction. Decimal numbers that repeat and terminate can be written as fractions as well. There are numbers that are not rational, and when something's not, it's the opposite. We call them irrational numbers. Irrational numbers are numbers that cannot be written as fractions. So they would be non-terminating and non-repeating decimals. The set of rational numbers and the set of irrational numbers together, so all of the numbers counted up, would be, they make up real numbers. And you're like, well, aren't all numbers real numbers? Later you'll get to numbers that aren't real, and they're notated with an I, but for now we're going to look at real numbers. And they're organized in a Venn diagram, which we've talked about as well, about how Venn diagrams can show what things are connected in a group and which things are separate from a group. So just some examples here of irrational numbers. Irrational numbers are numbers like pi, because if you know the number pi that we use when calculating with circles, that's a number that does not stop and it does not repeat. The decimals go on and on. So decimals that do not have repeating, so you usually label them, if you notice there's a couple digits, and then those digits don't repeat, and they put them with dots, showing that that number is going to keep going, and since there's no bar notation, there's no repeating. Rational numbers, again, are numbers that can be written as a fraction. So, for example, 3/4, because that's the same as 75/100. 3/10 repeating, because we could have this here, because we can write that as a fraction, as well as 1/3. So rational numbers, those are included here. Integers and whole numbers are also rational numbers, but they have their own categories as well. So if I think of integers, which we looked at in chapter 1, are my positive and negative. If you think full numbers, whole numbers, but they're not considered whole. So integers would be like -4, -12, the positives and the negatives, not fractions, not decimals, it's rounded out numbers. Whole numbers then, including 0, are our positive whole numbers. So they are counting numbers, essentially, the ones we go up with. So what this means is, to be a whole number, you have to first be real, then rational, then an integer, then a whole number. Integers then are real, rational, and integers. Rational numbers are real and rational. So you have to be able to fit all categories to get down to this final one. And then so you can list kind of what they are included as. So that's a little chart. You can add more examples if you'd like to. Your book will have some as well. And so it's kind of just a fun way to organize and kind of remember. And this is something you'll see in 8th grade again. It's very important that we remember how to categorize these numbers based on their what is made up by them. So we're going to name all the sets in which a real number belongs. And notice there's a study tip there on the side that says classifying numbers. Always simplify numbers before classifying them. Simplifying them meaning write them as, as this whole number or something, or whatever you can simplify to if there's an operation. So what we see for number 1 is that the decimal ends in a repeating pattern. So yes, the dots say it continues, but we could label this with bar notation because it is 25/100 repeating. And we know that repeating decimals, we can write them over 99 or whatever 9 place value they're in. So the decimal ends in a repeating pattern. It is a rational number because it's equivalent to 25/9. Since I can write it as a fraction, I know that it's rational. The square root of 36. Simplifying this would just be me saying that the square root of 36 is 6. And since 6 is a whole number, that means it had to have been an integer and a rational number as well. If we go through this kind of step by step, well, I can write 6 as a fraction. I can write it as 6/1. I can write it as 12/2. So it can be written as a fraction, so that makes it rational. It's an integer because an integer, remember, is those sets of the positives and negative whole numbers. So anyway, this way of a negative 1, and anywhere to the right of the positive numbers as well. So 6 fits in an integer category, and 6 is a whole number we can count with it. So then we look at the negative square root of 7. Well, you can use your calculator now, and so you would just type in using the radical symbols. So if I have the calculator up, for example, the square root, so I would plug in 7 and then take the square root, and on your calculator it'll show it stops, but really there is no repeat if you look at it. So since it is not a repeating and it does not terminate or stop, that means that this is an irrational number. So it's time to try on your own here. Square root of 10, I know it's not a perfect square, so I could type in on my calculator 10 and take the square root. I notice there's no repeating values, so it ends up to be something like bear with me, 3.1622776, and there's so many more repeat. It does not repeat, so that's going to mean that this is an irrational number. There's no repeating. For B here, I see that it's already written as a fraction, so that tells me that this is going to be a rational number for sure. So this is real. It's rational because of the repeating decimal, or the fraction that can be written as a decimal, but since it can be written as a fraction, I know that it's rational. That negative 2 there tells me that I could be looking at an integer, but it is not an integer because this is equivalent to negative 2 and 4/10, and that's not a whole number. That doesn't come in that set of positives and their opposites. So that is not an integer. So remember, this is not an integer just because you see a negative there because of that decimal place. So this is real and it is rational. For the square root of 100, hopefully we know that's a perfect square and that is equivalent to 10. I know 10 can be written as a fraction. So 10 is real. I know it's written as a fraction, so it's rational. I also know it's in my set of integers. And I know that 10 is a whole number. That's kind of messy. This not having a smartboard thing is messing with me. So that is what we consider there. You may be asked to graph real numbers. And so we're asking here, estimate the square root of 6 and the negative square root of 3 to the nearest 10th. Then graph those numbers on a number line. Another study tip here. It's helpful for us. Remember that a negative is always less than a positive number. So therefore we can automatically assume that this negative square root of 3 is going to be less than the square root of 6. So you can use a calculator here and just use that radical sign again to find out what it's equivalent to. So I get this type of number in my calculator, but it says round to the tenths. So I go from the hundredths, and 4 will leave my 2 and 4/10ths rounded there. 3 will leave my 7 rounded to 7. And so then I go to a number line, and 2 and 4/10 is a little less than halfway between 2 and 3. So I graph the square root of 6 there. Notice how I'm graphing my original number I was given. And then the same thing, negative 1 and 7/10 is the same as negative square root of 3, and I graph that there. Okay? So, and now we're just comparing them as well. So comparing real numbers using a less than, greater than, or equal to sign. So here, again, we can use calculator, kind of round them out. So square root of 7 is irrational, but it goes to this decimal. And 2 and 2/3 is a repeating decimal of 2 and 6/10 repeating. What I notice is that this number would not round, or it would round to 6 and 5. So that is actually less than 2 and 6/10 repeating. So my comparison is to use the less than symbol here. So 1 and 5/10 repeating is what compared to the square root of 2 and 25/100ths? Well, if I write the square root of 2 and 25/100ths as a decimal, it's actually perfect square of 1.5. So I mark it on the number line above 1.5. 1 and 5/10ths, though, repeating, is the same as that 5 repeating. So if I did round this would actually round up to 6. So that is actually going to be a little bit bigger. It's going to be halfway between these two decimals. That's going to be bigger than So then I can say that 1 and 5/10 repeating is greater than the square root of 2 and 25/100ths. A lot of math words here, I know. Just kind of keeping that number sense and that place value with you as you go through these things. Take the square root here to find a comparison. I did learn the other day that the square root of 6 and 25/100ths is a perfect square, and 2.5 is what multiplies to get there. I know 2 and 1/2 here is the same as 2 and 5/10, 2 and 1/2. So these two are equal to one another. And so you could put them on a number line. You know, you have your 2 and 3 here, and they're both going to be here at 2 and 1/2. So you could label your 6 and 25/100ths at the same place that 2 and 1/2 is located. Okay. So don't forget, rewatch the video, check out somebody else's video, look at the examples in the book, or check out those personal tutors on the online textbook. You guys are doing a great job. Keep up with that vocab. Bring with you your notes, 2 things you learned, 1 thing you're wondering, and do not forget to take the NICU assigned to you. Good luck.